Hi, good day to all. I'm Kow Wei Loon and today be presenting the INE 504 project and presentation, and the title is about LED. As you can see, this is the three journal which choose that related on GaN-based LED by method and material which can improve the LED. So the first one is the impact of strain layer superlative, which is SLS, to the emission and internal quantum efficiency (IQE) of a GaN LED. And second is the effect of dielectric distributed brush reflector on electrical and optical properties of GaN-based flip chip light emitter diode. And the third one is increasing the internal quantum efficiency of green GaN-based light-emitting diode by employing great quantum well and electron blocking layer. So for this is we'll start for the journal one. So we continue for the next. So you can see that this is the journal one of the executive summary. In this paper, strain layer superlative is a SLS is the alternative layer in structure composed by two different material. GaN LED by insertion of SLS can produce enhancement electron confinements and improvement of hole injections. Besides, SLS give in uniform electron distribution that can lead to high emission and efficiency. The research of this work is to investigate on total SLS thickness of 3 nanometer, 6 nanometer, and 9 nanometer respectively. Hence, the result has shown that LED in second period of SLS in lower current of 0.1 milliampere get total emission rate display linearly increase. However, it was discovered that third period with SLS in higher than 6 nanometer causes PN junction failure with no emission. Next, this is the research methodology for Journal 1, which is will use console simulation software to build the LED structure. Then after that, we will going for the GaN material added to every layer. Also use console doping concentration and thickness. And then next, we are going for the pattern substrate fabricated on GaN LED. First, we will form an N-GaN with the width of 700 nanometer with the thickness of 2 nanometer. Then second, deposit indium about 4% and gallium about 96% per GaN SLS with the thickness of 3 nanometer thickness. And third, we'll form P-type aluminum with the 20% and the gallium about 80% of ELB with the thickness of 20 nanometer. After that, we will going for form 2-layer P-type GaN higher dopant at topmost layer plus P and N side contact. Then after complete the structure of the GaN, then we will starting for the investigation. For the investigation, we will build a three GaN LED structure with the LAS1 with 3 nano thickness. Between that, inside got one set of indium 4%, gallium 96% per GaN SLS, and the second SLS is a 6 nanometer thickness with the two set of indium 4% and gallium 96% per GaN SLS. And the third one is SLS3 with the 9 nanometer thickness with the three set indium 4% and the gallium 96% per gallium SLS. With these three SLS investigation, we found out that the SLS1 and SLS2 with the thickness 3 nanometer and the thickness 6 nanometer will achieve the IQE and emission rate increase, and also achieve current and voltage increase. And this achievement will end process and done suggests that second period of SLS in 6 nanometer thickness will give better carrier transportation with low turn-on voltage and use smaller injection current. But In investigate on SLS with 9 nanometer thickness, it showed that the PN junction failed and no emission was observed. That this is will be moving to the need for the investigation and additional simulation need carried out to fine-tune the number of the LSS to get a better result to success. And this is one now. This page show the result and discussion about the strain layer superlative. Figure above show the current voltage curve for research on 1, 2, and 3 period of SLS that show the voltage increase. As the current increase, Figure A show LED with first period of SLS function turned on at voltage of 3 V, and Figure B is a second period of SLS operate at bias voltage of 2.5 V lower than the first period of SLS that operate at 3 V. At starting zero intersection, the curve increased progressively into the forward characteristics with lower current and voltage compared with the first period of the SLS. Besides, the active layer being occupied by the injection carriers when the bias increase higher than 2.6 V will lead to a dominant radiative combination. Hence, further forward bias of 3 V make current voltage characteristics be essentially omit. And continuously, it recommends that the second period of SLS with low turn-on voltage give good carrier transport in LED. However, the figure C for third period of SLS show the breakdown region where the PN junction fail of the reverse IV characteristics. Furthermore, with increasing SLS more than 6 nanometer in third period or more will affect the LED performance by obtaining good carrier transport. Next, this graph shows the total emission rates of the SLS. Figure above shows 3 different SLS of total emission rate profile which taken as a function of current. Figure A and B show the emission rate increase rapidly in both 1 and 2 period of SLS. As the result, the total emission peak is higher than 2.4 times 10 power by 12 in the 1 period of SLS. Compared with the second period of SLS is about 2.48 times 10 power by 9. Moreover, the figure above can observe that the second period of SLS function at smaller injection current compared with the first period of the SLS. However, the figure C period of SLS presents that the LED is not operating properly, which indicate an insignificant emission happened by consist value of emission rates of 47.5. Next, it will be internal quantum efficiency. Figure above show the LED of the internal quantum efficiency and the function of the current. The IQE curve above provide the proportion of the injection carriers that radiative recombine to radiate light and as ratio of the emission rate to carrier rate. As the result, both A and B with first and second period of SLS show similar result of IQE with increasing current, and IQE drops on figure B is more significant than figure A. However, figure C show the opposite result, which represent the insignificant result. Moreover, the figure A show that the IQE peak of first period of SLS by 4 times 10 negative power by negative 4 is higher than the second period of SLS by 8.7 times 10 power by negative 6. In order to realize the second period of SLS achieve IQE peak at current lower than 0.05 milliampere, better than the first period by 0.1 milliampere. After that, both IQE then dropped significantly. After that, Journal 2 Effect of Dielectric Distributed Brush Reflector on Electrical and Optical Properties of GaN-based Flip-chip Light-Emitting Diode. As for executive summary, there are two types of GaN-based with distributed brush reflector and without DBR to investigate the effect of dielectric DiO2 per SiO2 DBR on electrical and optical characteristics of flip-chip light-emitting diodes. As the result, the FC-LED with DBR shown 25.3% of light output power better than the flip-chip LED without DBR at 150 milliampere. Moreover, discovered that use of via hole-based N-type contact can spread injection current uniformly over the entire active emitting region. Furthermore, increasing current density of LED effective method to decrease the carrier lifetime and increase the modulation bandwidth. However, to further improve the performance of LED, need improve both light extraction efficiency and internal quantum efficiency. Second Journal of Research Metrology. By starting, need to build the GaN-based structure by using the TFCALC software to simulate it. First, to follow the sequence of the build, you need to build the first is a GaN-based LED by 20 nanometer. After that will be undoped GaN buffer layer by 3 micrometer. Then third will be CDOP and GaN layer by 2.5 micrometer. And the fourth will be 16 pair of indium 2% and gallium 98%, and with the thickness with 2.5 nanometer, and the GaN will be 2.3 nanometer. And 12 pair of indium 16% and gallium 84% by 3 nanometer, and GaN about 12 nanometer thickness, mounted quantum well. And the fifth, a low 10p GaN layer with the 20 nanometer. Then afterwards, will be from the PL GaN 15% and gallium 85% of the E as a EBL, the thickness by 45 nanometer. Then will be formed MG dot and P GaN layer with the thickness by 120 nanometer and active by annealing 750 degree at N2 atmosphere. As for here, is a form of the N-type via host. To form the N-type via host for the next process, we will use the ICP etching base BC3, CI2, and AR gas. Etching portion of P-GaN and in-GaN per GaN multi-quantum well to expose the N-GaN layer. Then next we will moving to deposit P-GaN layer with 200 nanometer thick of SiO2 by using PECVD. Next will be form stripped SiO2 by optical photolithography and buffered oxide etch. And next, deposit ITO 115 nanometer thick on P-GaN as P-type omit by using electronic beam evaporite plus thermal annealing 550 degree under N2 ambient. And continuously will be deposited on a C, R, AI, TI, PT, AU by the thickness of 20 nanometer, 100 nanometer, 50 nanometer, also 50 nanometer and 1 micrometer metal on ITO. Next will be formed another N-GaN layer for P and N electron. Then deposit 14 pair of TiO2 per SiO2 on ITO by using ion beam subsputtering. Onwards will be evaporized by CR, AI, TI, PT, PI, PT, AU by the thickness of 20 nanometer, 100 nanometer, 50 nanometer, 50 nanometer, another 50 nanometer, and the last 50 nanometer and 1 micrometer into P-type and the N-type via hole SP and N-PAIN. After completing the outer structure, we'll be moving on the investigation. By the investigation, we will be divided to two types, which is with DRB and without the DRB. While the structure with the DRB is significantly achieve the IQE, LOP, and EQE increase. Therefore, the increasement that will be complete with the DRB achieve light output power by 25.3% at 150 milliampere. But if without the DBR, it will achieve the thermal conductivity. So for the thermal conductivity, it will complete without the DBR, exhibited higher lighter output saturation current. So for the result that not successfully with the great DRB or with the DRB, so the flow will be going for the no, then will fall on the investigate and analyze for improvement and going forward on this of the structure to find the solution. Next will be discuss about the result and the discussion of the DBR. Figure A show the flip chip LED with and without DBR of the current versus voltage. As the result, the fault voltage of the flip chip LED with and without DBR were 3.11 volt and 3.03 volt at 150 milliampere. Meanwhile, Figure B show the flip chip LED with and without DBR of the light output power versus current and external quantum efficiency versus current characteristic. As the result, the light output power of the flip chip LED was 204.6 milliwatt by 25.3% with DRB higher than flip chip LED without DRB was only about 152.8 milliwatt at 150 milliampere. In order to realize by insert use of DBR have high reflectance in blue light wavelength region. Moreover, the corresponding EQE of flip chip with DBR was 49.5%, while without DBR was 39% respectively at 150 milliampere. This result also show that the EQE of the flip chip LED with DBR achieved 21.2%, higher than without DBR. Hence, the light output power of flip chip LED with and without DBR were 875 milliampere and 1025 milliampere respectively due to DBR as the dielectric DiO2 per SiO2 has low thermal conductivity. However, flip chip LED without DBR produce higher light output, saturation current, and better heat dissipation performance in flip chip LED. Moreover, Journal 3, increasing the internal quantum efficiency of green GaN-based light-emitting diode by employing grounded quantum well and electron blocking layer. As for executive summary, the single quantum well device became promising for efficient green indium gallium-based light-emitting diodes. When it enters at lower current density, it shows significant drop reduction at high current density. Normally, the indium gallium per GaN layer is used as an emission layer. The lattice misalignment of an emission layer is mainly attributed to the result decrease on IQE. After that, by increasing the content of indium in indium gallium, the aggravated happen on the difference of lattice constants between EP layer. Moreover, the granted electron blocking layer become easier for the injection of hole into the active region and granted quantum well boosted radioactive recombination. And here is will be see that this is the journal 3 that the research methodology. And by this methodology also will be built. You need to build the LED structure, but is using the APSYS system. Also is a simulation software to build the structure of the LED. First, we will build on the quantum well and the quantum barrier will be fixed our structure in 2.5 nanometer and 10 nanometer. Next will be moving to the active region where we set the thickness will be 22.5 nanometer. Then next will be build an N gun and P gun with the thickness of 3 micrometer and 0.15 micrometer. Next will be setting the doping concentration in 5 times 10 power by 18 cm and 1 times 10 power 18 cm. Then will be set all structure coefficient as RH and Auger recombination by 2 times 10 power by negative 7s and 5 times 10 negative power negative 31 by cm 6 power by 6 per s. And next will be P dot and ELB. Then the concentration will be set by 3 times 10 power by 17 cm power by negative 3 and the thickness will be 0.020 micrometer. After complete all the structure of the GaN-based LED, then we'll be starting for the investigation. So the investigate will divide into 4 kinds of the LED that will be different. Will be between is the LED 1 will be got 30% content of indium and 50% composition of aluminum. And LED 2 will be increasing indium by 25% to 35%. And LED3 will be increase the aluminum by 0 to 15%. And lastly, LED4 will be increasing both indium 25% to 35% and aluminum from 0 to 50%. As for the result, the 4 of the LED will achieve the highest IQE and light output power and also current density among all. But for the result, we'll get the LED4 that recommended LED4 for both indium for quantum well and aluminum for EBL will get the highest yield of radioactive recombination amplified improved. But for the others of the LED will achieve not so high, so the flow will be moving to know as the investigation and the analysis for the improvement on EBL or quantum well. We are moving to the PDOC EBL or the quantum well and the quantum well barrier for further investigate to get some to get improvement. As a result and discussion, this is about as a figure. As you can see, this is the figure A and B show the comparison of the electron and hole concentration across the active region, and also non-asymmetry characteristic of carriers. Figure C show the comparison of radiative recombination of all LED. Subsequently, the asymmetry has the stark difference between the electron and hole confinement in LED1 by figure A and B. The shaded area above figure B show the confinement of electron at the interfacial region between quantum well and electron blocking layer. LED 1 and 2 is observed for electron leaking from the well by replacing of conventional EBL with granted EBL show the quantum barrier and electric quantum barrier interface become smooth. LED 4 show highest concentration of holes compared with other LEDs 1, 2, and 3. Moreover, LED 4 also enchants 50% higher than the 1, 2, 3. In this observation can result that the hole injection more favored on LED4. After that, figure C show also LED4 get best radiative output as granted quantum well and electric block layer. The granted quantum well can improve of the injection of hole and granted EBL can reduce the overlapping of the electron and improve hole wave function. The figure C also shown the relative recombination of LED4 is amplified by 46%, 28%, and 10% by comparison to the rest of the all device structure. Next will be comparison of IQE with light output power and the current voltage characteristics. So figure above of the A show the comparison between IQE and the LOP for all LED. The LED4 has observed to be the best IQE among the all LED. In active region, IQE is the ratio of total output of photon to the concentration of inject carriers. After that, figure A shows that the effectively drop is 62%, 58%, 46%, and 31% at 100 Armstrong cm power by -2 for LED 1, 2, 3, 4 respectively. Moreover, light output power for LED4 also shown that in figure A is the highest among all other structure, and light output power of proposed structure is enhanced more than twice. Meanwhile, figure B shows that the comparison between the current and the voltage. It has been reported that the turn-on voltage of grounded quantum well and grounded electron blocking layer has been reduced. However, by comparison with conventional structure, the grounded layer by the earlier turn-on voltage of our device is reportedly literally example like LED 2, 3, and 4. By overall the comparison that these three journals that we can divide into the novelty method and the result. For the first journal of the LSS of the novelty, it is granted that the SLS lead to high emission and the efficiency of the IQE of GaN LED. And the method is to using console to simulation on GaN LED with SLS structure and investigate by form 3 period with different thickness of indium per GaN by 3 nanometer, 6 nanometer, and 9 nanometer. And the result get the SLS granted total emission rate displayed linearly increase. And second period of the SLS provide good carriers in transport in LED by low turn-on current in 0.1 milliampere and voltage in 2.5 volt. Third period show fail with no emission if the thickness of the higher than 6 nanometer. As for journal 2, for the DBR for the novelty is granted, give promising improvement on IQE, LOP, and EQE on flip chip LED. So the method is to use the TFCALC to simulate it on GaN LED structure with DBR. Then the second is a form 14 alternative nanometer thick layer of silicon dioxide and titanium dioxide. And the third will be the form via hole-based N-type contact to spread the injection current. So for the result for the DBR, will be granted high mechanical robustness and high reflectance by over wavelength range mechanical robustness and high reflectance by over wavelength range about 400 nanometer to 600 nanometer, and the peak wavelength of the flip chip is about 465 nanometer. At 150 nanometer, the LEE output power is with DBR improved about 25.3%, and by granted double DBR also achieved more higher reflectance in 97.8% at 465 nanometers. As for the last one, is the journal 3 is about the EBL and the quantum well. If granted the structure for the novelty, the structure to improve the internal quantum efficiency of green GaN-based light emitting diode. As for the method, they use APSYS to simulate on the GaN LED structure with EBL. Then second, the EBL by increasing composition of element from 0 to 15%. And quantum well by increasing component of indium from 25 to 35%. As for the last result for the EBL is granted improved injection of hole into the active region become easier and the radiative recomposition boosted due to granted quantum well. The quantum well granted to reduce the electricity field for entrancement for overlapping of electron and hole. Next, it will be the overall conclusion of the three journals. For the first journal of the LS, to summarize, the SLS thickness of 6 nanometer on 2 period among of others 2 thickness produce better efficiency operation of GaN LED by low bias voltage in 2.5 volt, and total emission rate also rapidly increased high emission. Besides, the IQE also shown in low driving current. However, the IQE drop decline significantly observed by third period lead to PN junction failure and no emission when thickness is higher than 6 nanometer. As for second journal, for the DBR, the GaN-based flip-chip light-emitting diode by granted combine of two single TiO2 per SiO2 DBR stacked into double DBR exhibit high reflectance of 97.8% at 465 nanometer. Moreover, improvement on via hole-based N-type contact increased the current spreading of flip-chip LED. To summarize, light output power of flip-chip LED with DBR increased 25.3% compared with flip-chip LED without DBR. However, low thermal achieved by flip-chip with DBR compared with flip-chip without DBR. Last journal of the conclusion is about the EBL. So the EBL of the conclusion is in this study, it has been observed that a single quantum well show promising result for the efficacy green indium gallium-based LED. By granted EBL, aluminium by 0 to 15% and granted quantum well by indium 25 to 35% show improve on hole injection and overlapping of electron hole wave function of green GaN-based LED. As for overall summarize, the third journal was studied and investigated to implement the material and method to improve the light extraction on GaN-based LED. Among the best chosen one was recommended on DBL on journal 3. Granted, DBR significantly improved both IQE and LEE, which is promising material in flip chip technology. DBR have high reflectance of arbitrary angle and better heat dissipation. Besides, it can be operated in higher injection current density compared with top emitting LED. Moreover, DBR also important for the role for high performance vertical cavity surface emitting laser. Furthermore, DBR double DBR stack exhibit a high reflection of 97.8% at 465 nanometer. Lastly, DBR have high reflectance in blue wave range and can use a reflecting ohmic contact for flip chip LED. That's all for my presentation and thank you.